Welcome to Mahatma Education Society's e-learning channel. This is the lecture 4 of a series of lectures on Introduction to Mechanical Vibrations. The outline. We will look at the recapitulation of last lecture and vibration terminology. The recap. In the basic concepts of vibration chapter, we had seen the minimum number of parameters required so as to cause vibrations. So we had seen that the mass and the spring are compulsorily required so as to cause vibrations. The mass was responsible to cause kinetic energy, while the spring was responsible to cause the potential energy, and that there was the reversibility of these energies which was causing the vibrations. The damper was required or may not be required in some cases. So the requirement of damper was solely to dissipate the energy in the form of heat to the surroundings. In the phenomenon causing vibrations, we had seen the reversible nature of the energies from kinetic to potential and potential to kinetic, and this was causing the vibrations. Now let us move over to the vibration terminology. We will look at all the definitions and some basic concepts which we will be revisiting in the future chapters. The first of these is the periodic motion. Any motion in which the time taken for each cycle is remaining constant, that is a periodic motion. Hence, I can say that the time taken for completing one cycle of motion is remaining constant for each cycle. So I can have different examples. So the time taken for completing one cycle is the same. So this time, all times are same for every cycle. So this is one of the examples. This is a simple harmonic motion. Likewise, you can have different examples, different waveforms, something like this. The time period is the time taken for one cycle. That's simple. Frequency. We have two types of frequencies. One is called as the linear frequency, while other one is called as the circular frequency. And we have some definite relation between the two. Suppose we are talking about one cycle, cyclic motion. So we know that pi radians is equal to or corresponds to 180 degrees, and 2 pi radians corresponds to 360 degrees, which is one cycle. Now if you are talking about the number of cycles covered per unit time, that is second, we denote it by the symbol small f, that is the linear frequency. So this one is small f. I call it as cycles per second, or I call it as hertz. In short, I will write it as Hz. So the number of cycles covered per unit time, it is the linear frequency. I got correspondingly the amount of radians or angle covered per unit time, that is nothing but the angular frequency, which I denoted by omega, radians per second. So we have a basic relation here. We can cross multiply these two. So we can have omega, that is omega multiplied by 1, that is omega is equal to 2 pi multiplied by f. So we have one very basic relation between the frequencies, the circular and the linear. So omega is equal to 2 pi f, or f is equal to omega divided by 2 pi. So we have to use this number of times. amplitude, it is the maximum displacement of a mass from its mean position. Maximum displacement of mass from the mean equilibrium position. Suppose I am denoting the motion something in this manner. This is the displacement, say denoted by x as a function of time, and this is the time. So in any one cycle I am having the maximum displacement of the mass, that is called as the amplitude. Let us say it A. Now what is meant by free and forced vibrations? So free vibrations also is called as natural vibrations. So we have taken earlier the example of spring and mass system, mass and spring, and if I disturb it either by giving initial displacement x naught and or initial velocity x dot naught, we induce some kind of energy in the system so as to initiate the vibrations. So once vibrations have started, then there is no requirement of any external agency so as to continue the vibrations. So vibrations, I say that they are occurring inherently or due to its own inherent properties. So internally what is happening is there is a conversion of energies taking place from kinetic to potential and vice versa, and there is no requirement of any external agency or force. So I can say that for free or natural vibrations I am having the force as a function of time is absent. So the vibrations are occurring freely or naturally, right? And in case of force vibrations, I require the presence of some external agency or a force. We call it as excitation in vibration terminology, so that vibrations are occurring continuously. So the input to the vibrating system is a force, so it is not equal to 0, right? This is a force vibration and this one is a free or natural vibration. Natural frequency. So we are talking about the natural vibrations, and the frequency of natural vibrations is called as the natural frequency. That means the frequency corresponding to no force is called as the natural frequency. We are having two types. One is called as, in the absence of damping, we call it as undamped natural frequency. There is no damping as such. We denote it by omega suffix n. N stands for natural. And in the presence of damping, we call it as omega suffix d, in the presence of damping. So later we will see what is the relation between omega d and omega n. But both are associated with the free vibrations. Free vibrations in the absence of damping, and free vibrations in the presence of damping, right? Simple harmonic motion. Sometimes we also call it as harmonic motion, to be simple. So in short, it is Ch.1 motion. Suppose we are talking about some cyclic motion. So we have a circle. We imagine that we are having a particle P that is moving around the periphery of this circle or the circumference of the circle with uniform speed or uniform velocity or uniform motion. So after some time, the P is occurring taking a new position, say P dash. So this is the angle covered. So I am taking the reference axis as this x axis. So theta is equal to omega t. Now the motion of the particle p about this circumference is the uniform velocity motion, but now if I take the projection of this particle p while it is in motion along the diameter of the circle. So, this one is the projection of the particle p along the diameter. So, the motion of this projection along the diameter defines simple harmonic motion. So, we have taken the projection of this particle p along the vertical diameter. Likewise, we can also take the projection of particle p along the horizontal diameter. In that case, the projection will be over here and the particle projection will be moving from this end to this end, right. This also defines simple harmonic motion. Suppose I am taking the projection of the particle along the vertical axis. So, in that case, this becomes the displacement as a function of time t, and I can imagine that the center of gravity of the mass is corresponding to the projection of the particle along the diameter, and we can visualize that it is connected with a spring over it. So, the mass will be having a motion between these extremes from here till here. These are the extreme positions and this becomes the equilibrium position, the middle one, right. Likewise, if you are talking about the simple harmonic motion in a horizontal sense, then I can imagine that we have a mass over here, the projection of the particle, and then we can associate some spring at one of the ends, and the moment of the mass will be restricted from here to here, right. So, this also is a simple harmonic motion. So, in the first case I can write the displacement equation as this, let us call this as the amplitude A. The radius of the vector defines the amplitude. Why? Because if you look over here, from here till here, it is the maximum displacement from the mean position. So, it becomes the amplitude. So, amplitude times its sine of the angle theta or omega t. So, I can write x of t as a sine of omega t, or if I am talking with respect to the horizontal moment, I can call it as a multiplied by cos of omega t, right. So, presence of sinusoidal term sine or cosine indicates that we are talking about simple harmonic motion. If we separate out the sine term or cosine term, which give us a variation in the value of this parameter, which is the displacement between 0 and 1 values. So, this provides a variation in the value of the parameter, that is displacement over here, right. Separate out these terms, sine and cosine terms, what remains is the amplitude. So, this is one of the important things you have to remember. We can express any parameter other than this displacement. It can be velocity, it can be acceleration, it can be force. So, as long as they are functions of time and they are harmonic in nature, so I will be having this sine and cosine terms in those equations. So, what you simply do is remove or separate out the sine terms or cosine terms, which give the variation in the value of the parameter, and whatever remains apart from the sine or cosine, they are nothing but the amplitudes. So, I can have displacement amplitude over here. This is the displacement amplitude to be precise, right. Likewise, if I am talking about other parameters, say velocity, I will be having velocity amplitude. Then if I am talking about acceleration, it will be acceleration amplitude, and similarly for force, I will be having a force amplitude. Okay. So, amplitude itself indicates it is the maximum value for some value of the for some parameter. Okay. Now, how can I define this simple harmonic motion? I can define this in the following way. The motion of the projection of a particle along the diameter of a circle if the particle itself moves with uniform speed along the circle, and that motion of projection defines the simple harmonic motion. This is one of the definitions of simple harmonic motion. Okay. So, for the second definition, we have to refer to this equation, right? X of t is equal to a sin of omega t. Now, suppose I take the derivatives of this with respect to time. I am having here omega a cos of omega t. So, in this case omega a separates the cos term. So, cos gives us the variation, omega a is the amplitude for velocity, it is the maximum velocity in that cycle. Likewise, if I take one more derivative, I am having d2 x by dt square, that is x double dash or x double dot is equal to minus omega square a times sine of omega t, and I know that a sin of omega t is nothing but displacement itself from this definition, right. So, it is minus omega square x. So, I am having here acceleration is directly proportional to the displacement, but opposite in direction, because I am having a negative value over here, right. So, the other definition of simple harmonic motion is the motion in which acceleration is always pointed towards the mean. So, why mean? Because here I am trying to represent the x something like this from the mean. So, the acceleration will be always opposite to the direction of displacement. If displacement is in this direction, then acceleration is opposite. So, always you are saying here that the acceleration should be pointing towards the mean, right. So, the second definition of simple harmonic motion will be the motion in which the acceleration is always pointed towards the mean. Resonance. Now, we know what is meant by the undamped natural frequency omega n, or in terms of linear coordinates it is Fn, linear natural frequency. Now, this will be a constant value for the system once designed. Okay. So, I am having mass and stiffness characteristics of the system, and later you will see that to find this omega n we will be requiring the values of spring and mass characteristics. So, once they are designed, the value of this omega n will be practically constant. So, there will be no change during the operation of the particular machine or the system. I can make use of one external force, it can be a motor, right. It can be motor so as to provide the motion to the particular product, right, and normally the input is in the form of rotational motion, that is a uniform angular velocity omega. So, this is the excitation frequency or the forcing frequency. So, I can change the value of this forcing frequency as per my requirement. So, the value of this may range from 0 value to some maximum value, right, during the course of operation. So, this is a variable thing, but once designed omega n will remain constant. So, whenever this omega happens to be equal to omega n or it is very close to it, then we have a condition called as resonance. So, why resonance is very important? Because the amplitudes set up during resonance are very high, right. So, because of higher amplitudes I am having a lot of deformations in the elastic bodies, and hence I am having the lot of stresses induced, and they might go beyond the permissible stresses in the materials, which may be a cause of failure. So, understanding the resonance or the natural frequency is very important for us, okay, so that we can design the input motor requirements as per our requirements, or for a given value of operating speeds I can design what should be the value of mass and stiffness over here, right? Damping, so this has been explained earlier. It is the mechanism to dissipate the energy in the form of heat. Now, degrees of freedom, in short, DOF. So, it is the number of independent coordinates, sorry for this, it is a minimum number of independent coordinates required to specify the motion of entire system. Okay. So, what is meant by this? Minimum number of independent coordinates. So, we take one small example here. Let us have a disk, and let us have a spring over here, a thread that is rolled over the disk, right, and let us have a mass. So, this is having mass moment of inertia about this axis O, and mass is having some linear motion x. So, this is theta, this is k, right. Now, I can write kinetic energy for the system for both the masses, in fact. So, one is in terms of rotational motion of the disk, half into I about O axis into angular velocity square plus half into mass into linear velocity square, right. So, here I have written the kinetic energy in both the coordinates, but I know from here that for a definite moment of the mass, that is x, I have some definite moment of this disk, that is theta. That means both these masses are related in terms of motion, or I can say this is the kinematic or motion wise relationship. So, kinematic relationship exists. So, I can form one relation here kinematically. I can say x is equal to, let us say the radius is r times theta, or I can convert theta in terms of x, theta is equal to x upon r. So, likewise here in these equations I want the derivative. See, you can get the derivative like this. Okay. So, basically you can convert these two coordinates in terms of only one coordinate. Why? Because I am having a dependency in terms of motion. So, I think it is clear, right. So, here minimum number of independent coordinates, they are only one, even though I am writing here two different coordinates, but they are dependent in terms of kinematic relationships, right. So, basically in terms of independency it is only one coordinate, right. Now, suppose if I am having a spring over here, it is something kind of a rubber band, right. Now, I cannot say that by moving this by certain distance I will get the definite value of theta. That is not possible. It depends on the amount of stiffness of this particular spring, right. So, this may be having more motion or less motion, it depends. So, in that case, in the presence of spring I cannot say x is equal to r theta, that assumption will be wrong. So, this is wrong here. So, there is no kinematic relationship existing between this mass and this mass when we have a spring in between them or flexible elements between them, right. So, in that case minimum number of independent coordinates becomes 2, right. So, it is x and theta both are independent in this case, fine. One more example, I can have something like this. So, it is normally asked in the vivavos or orals, something like this. So, the question will be how many number of degrees of freedom does this system have. So, what should be your answer? So, you should say that because I am having flexible elements over here and over here. Okay. So, let us give some coordinates x1, likewise x2, x3, x4 and x5. So, even though I am showing 5 coordinates, but these 3, that is x2, x3 and x4, they are the one and the same because we have a rigid connection, right. So, x2 equal to x3 equal to x4. So, basically it is only one coordinate, and then x1 is not equal to x2 or x3 or x4 because I have some spring in between. The same case over here. So, basically I am having coordinate number 1, 2 and 3, so it becomes a 3 degree of freedom system. So I hope the concept is clear to you. Aperiodic motion. So we have seen what is meant by periodic motion, a motion where the time period for each cycle remains same in every cycle, right? Now aperiodic motion, A is a negative prefix, so it is different than the non-periodic motion. Non-periodic indicates that the time period is not same, something like random vibrations, right? So aperiodic motion is a motion where not even a single cycle of oscillation takes place. Not even a single cycle of oscillation takes place. So this happens for damping, which is the value of which is very high. So very high damping. So this high damping, actually I am speaking in terms of crude terms, vague terms. So technical name is a different one, we will see it later. Or I can have something like medium damping, right? So for these two kinds of dampings, we have mass once disturbed returning to the rest position without any oscillation. So it might be returning back, so it is time and this is displacement, right? So there might be the crossing of the mass to the other side of the mean position, but it may not come back to the same side of the mean position once disturbed. So there are a fair bit of chances of happening like this. So this one or this one, the mass may remain in the same side or on the different side, but it will not come back to the same side, right? So the point to remember here is there is no single cycle of oscillation or vibration. So what does it mean? There is no omega as such, right? So omega exists only if there is a one cycle of oscillation. Hence, if there is no omega, there is no time period also, right? So this indicates a negative prefix A. So aperiodic motion is a motion where there is not a single cycle of oscillation. Now mode of vibration. Now we are going into the multi-degree of freedom systems where degree of freedom is more than 1. So it's basically 2, 3 or 4, right? So what do you mean by mode of vibration? So in plain terms I will write it as the configuration attained by the body or system, okay, bodies or system when it vibrates with any one natural frequency, right? So concept is that if I am having 2 degrees of freedom, then it has 2 natural frequencies. If it is having 3 degrees of freedom, it has 3 natural frequencies likewise, right? So the system may vibrate with any one of the frequencies, and if it vibrates with any one of the frequencies, then what is the position attained by each and every mass, right? Suppose mass 1 goes over here, mass 2 may be moving over here, mass 3 may be moving over here. So we normally associate the movement of the first mass as having +1 in some direction with the unit value of movement, and the movement of the other masses are spoken with respect to the movement of the first mass. So it's in relative sense. So relative sense, so regarding the values it might be say 0.7 minus and plus 0.2, something like this. So plus indicates the direction here, minus indicates the opposite direction, okay, and I can also speak with respect to the values in comparison to the movement of the first mass. So this configuration is called as a mode shape, right? Mode shape. So node is that place in a vibrating system. Sometimes it may be along some location in the spring, right, where there is no deformation at all, right? So this is a node, this is a node, right? So we'll learn all these things in the multi-degree of freedom systems. A fundamental or basic mode of vibration Now we know that for multi-degree of freedom systems, suppose I'm having n degree of freedom system, so I'm having number of omega n's as n, omega n1, omega n2, omega n3, likewise I'm having omega nn, so corresponding to n degree of freedom, right. Now all these values are constant values. Once designed, then this all will be practically constant. I am going to use some motor for running up the machine. Okay, so the excitation speed will be omega, and I can range the values from 0 to some maximum value. Now whenever this motor speed matches with any one of these frequencies, I have resonance. So I am having practically n number of resonances, as there are number of degrees of freedom, right. Normally what we do, we sort all these omega n's in order, starting with the lowest value. So lowest omega n, which might be 0 sometimes, which may not be 0. Okay, so equal to 0 or not equal to 0. So depends on the case. Then we have the increasing values of omega n's. So it can run in very large numbers, right. So whenever omega matches with any one omega n, I am having some resonance, right, and corresponding to that resonance I can have some particular mode shape, right. So when I am having the first mode, that is omega matches with the first omega n1, right, then whatever configuration is attained, that is called as the fundamental or basic mode of vibration, and this is the most important of all the modes. Okay, so why it is most important? Why only a first few modes of vibration are studied? So this is one of the questions here. Okay, so this is the other way we have put up the question. So as a designer, only the first few resonances are studied, maybe around 5 or 10 resonances or mode shapes are studied, and we are not selecting the remaining ones. So there are a couple of answers to this. One is the motor speed is practically limited. Motor speed is practically limited. So what happens with this, right? So motor speed is omega, right, natural frequency. So it is having some maximum value, 0 rpm to some say 10,000, 20,000 rpm. Okay, so beyond that is not possible to be used, right. So the number of possible resonances within this 0 to say 10,000 rpm. Okay, so the chances that this will be matching with any one of these or any number of these will be limited, right. So suppose I am having omega n1 as some value 0 or 10, this might be say 100, 1000, something like. So it's just a number, right. So these omega n's, the higher numbers will be very, very large values. So obviously this omega may not match with the higher values, right. So this is one of the reasons why we study only a few of the natural frequencies or mode shapes or resonances, right. Second one is for low values of omega n. Okay, earlier we had seen in the introductory lectures that for large amplitudes we have very less frequency of motion, right. For large amplitudes we have less frequency. There is a relation between them. So we had seen the example of a large bird, then a small bird, eagle, pigeon, sparrow, likewise the insects, all those, right. So I am having some relation here. For low omega values, the amplitudes are generally larger. Okay, so if you talk about omega n low values, so if you are talking about very high values of omega n, the frequency is very great or a very large value, and there is a corresponding decrease in the amplitudes. Amplitudes are small, right. So only the first few resonances are studied. Why? Because we are dealing with the large amplitudes that are causing large deformations, and large deformations will induce stresses, and which are required to be checked with the permissible stresses, right. And if you are going for a studying of the higher frequencies, we are generally dealing with the very low values of the amplitudes, and this is not a concern, right. So only first few natural frequencies are studied, and these are the possible reasons for that. So in this lecture we have seen various definitions, that is the vibration terminology, and all these concepts will be revisited a number of times in the coming chapters. Happy learning. Thank you.